This is section 9.1, day 1, and we're going to start out by talking about sequences. A sequence is a function whose domain is a set of positive integers. So positive integers, 1, 2, 3, 4, 5, so on. We have a sub 1, a sub 2, a sub 3, a sequence of numbers. A sub n is called the nth term, and we denote the sequence with curly brackets, with a sub n. Example, write the first 5 terms of the sequence. The first 5 terms would be 3 to the first, 3 squared, 3 to the third, 3 to the fourth, and 3 to the fifth, which is 3, 9, 27, 81, and 243. On this one, we have factorial, so we need the first 5 terms, 2 over 1 factorial, and then 2 over 2 factorial, 2 over 3 factorial, 2 over 4 factorial, and 2 over 5 factorial. That is 1 factorial is 1, 2 factorial is 1 times 2, so that's 1. 3 factorial is 1 times 2 times 3, that's 2 6, which is 1/3. 4 factorial, if we take 6 times 4, that's 24, and then if we have 2 over 24, that'll be 1/12. And then if we take the 24 we just got with 4 factorial and multiply by 5, we get 120, and then 2 over 120 is 1/60th. So there's the first 5 terms of that sequence. Arithmetic sequence. Each term is found by adding to the previous term. So the key here is adding to the previous term. The value added is called the common difference. If we had the number 6 and we're adding on 4 and got 10, then we'd take 10 minus 6, so the common difference is a value of 4. The explicit formula for an arithmetic sequence is a sub n equals a sub 1 plus n minus 1 to the d. So you might see something like a sub n equals 5 plus n minus 1 times 6, let's say. So that's the kind of function that we're looking for. Geometric sequence. Each term is found by multiplying to the previous term. The value multiplied is called the common ratio. Explicit formula, a sub n equals a sub 1, r to the n minus 1. Write an expression for the nth term. To find each term, we're adding 5. So the common difference is 5, and a sub 1 is equal to 3. A sub n is equal to 3 plus n minus 1 times 5. And we could do a little math on this, and we would get 5n minus 2. On letter B, we have 5, negative 15, 45, negative 135, so on. To get the next term, we're multiplying by negative 3. So the common ratio is negative 3, and a sub 1 is equal to 5. So a sub n is equal to, we have 5 times negative 3 to the n minus 1. There's not much you can do with that, and you cannot take 5 times negative 3 and get negative 15, because that would not follow the order of operations. We'd have to do the power first. On the next one, it's not arithmetic and it's not geometric. This one is just the powers of n. So a sub n equals not powers, but n squared rather. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on. On letter D, we have a sub n equals, we have 3 to the n and then plus 1. 3 to the first is 3, and then plus 1 is 4. 3 squared is 9, plus 1 is 10. 3 to the third is 27, plus 1 is 28, and so on. Sequences on a graphing calculator. Sequences can be graphed on any graphing calculator by using parametric mode with a t-step of 1 with the graphing mode set to dot instead of connected, or by using sequence mode. If you have a mixture of types of graphing calculators in your class, I would have the students graph their sequences in parametric mode. And of course, this is written for the teacher of the class, but I wanted to show you this page. And we're going to work with parametric mode. And if you want to play around with sequence mode, it's in your notes. By all means, give it a shot. Let's look at an example on the calculator. Our example, the sequence is n over n plus 1. This is working with parametric mode on this particular calculator. Now if you go to mode, this is probably what your calculator looks like, and we want to go down to parametric, and we can get out of that, and then go to y equals, and in x on all of these we're just going to put t. That way it plugs in 1 and then 2 and then 3 and then 4. It plugs in the positive integers. Then the function is actually going to go into y1. So in this case we have t divided by parentheses t plus 1. And now let's talk about the window. We go to the window, we want the t's to go from 0 to, let's say 20 in this case, and that's what they've written. They've written the 20 right here. And then the step, since we want the positive integers, we want to plug in 0, 1, 2, 3, and we really don't even want to plug in 0. But let's go step of 1, and then in this case we're going from -1 to 20 for the x's, and going by 1s is fine. And then with the y's we're going from -1 to 5, and we'll go by 1s on that as well. Now when we graph this, sometimes, well, I didn't change it to dotted. This is the connected, so it will draw the line. It'll connect all the dots. If we go back to mode, we don't have every value. We only have the values we get when we plug in 1, 2, 3, 4, and 5. So we want to go, and we just want the dots. We don't want them connected. So now when we graph this, we have the dots, and we can see this one is leveling off to a value of 1. Calculus BC Lab on investigating sequences. Let a sub n be a sequence of real numbers. Here are the possibilities that could happen. If the limit as n approaches infinity of a sub n equals infinity, then we say that a sub n diverges to infinity, or we can just say it diverges. If the limit as n approaches infinity of the sequence is negative infinity, then we say that the sequence diverges. If the limit as n approaches infinity is actually equal to a value, then we say that the sequence converges to the value c. If the limit as n approaches infinity of a sub n oscillates between two numbers, then a sub n diverges by oscillations. So our sequence could oscillate between, let's say, 1 and 2. It could have a value of 1, then 2, then 1, then 2, then 1, then 2. And we don't say that this is leveling off to two values. We just say it's not leveling off. It's not converging to a value at all. Use your graphing calculator to determine whether the following sequences converge or diverge. Look at both the graph of the sequence and the table of y values as n increases from 1 shooting off to infinity. So to save time, rather than plugging all these into the calculator, I've already done that, and then we can just talk about the graphs. So this one seems to be leveling off to a value of 1. That's exactly what's happening. So this one converges. We can say not just 1, but we can say converges to 1. Let's go across rather than down. Let's look at number 6. This one is actually leveling off to 0. So this one converges to 0. And on number 2, when we plug it into the calculator, this one also converges to 0. Number 7, this one is clearly shooting off to infinity. So this one, we just say diverges, is just fine. That's fine as an answer. Number 3, this is the one that oscillates. And when n is odd, we will be adding -1. When n is even, we add +1. So this one will go between 4, and then we have 3 minus 1, 4, and 2. So it goes 2, 4, 2, 4, 2, 4, 2, 4. This one diverges, diverges by oscillation. Number 8, when we graph this one is oscillating, but it's getting closer and closer to 1. So this one is actually converging to a value of 1. Converges to 1. On number 4, this one is leveling off to -1/2. Now with just the dots, it's kind of hard to see that, but if you would look at the table, we could definitely see that it's leveling off to 0.5. So this one converges to 1/2. On number 9, this one is oscillating, and they seem to be getting farther apart, and that's actually what's happening. They are getting farther apart. This one diverges, and it diverges by oscillation. Number 5, this one is actually leveling off, so this one converges. Number 10, this one also levels off, and the interesting piece about this one is this. Let's pick a big value for this function. Let's say, I don't know, 10,000. We have 1 plus 1 divided by 10,000. Let's get that value, and then we'll raise it to 10,000. And we have 2.718. So this one is actually leveling off to E. This one converges to E. If a sequence has a finite limit as n approaches infinity, we say the sequence converges. If a sequence does not have a finite limit as n approaches infinity, then it diverges. Example, determine whether the following sequences converge or diverge. We have the limit as n approaches infinity of n over n plus 1. And really this is infinity over infinity. We could certainly use L'Hopital's rule, but how about we just use our ending behavior rules? Now the powers are the same, so this is equal to 1, and so this sequence is converging. It converges. On letter B, we have 1 over 2 to the n. The limit as n approaches infinity of this one is 1 over 2 to n, which is really 1 over infinity, and this one actually converges to 0. So we would say that this one converges. On letter C, this one, now I'm not sure how we're going to do the limit on this one or make any kind of limit statement, but this one is going to oscillate between 3 plus 1 and 3 minus 1. So it's going to oscillate between 4 and 2. On letter D, and we'll say that this one diverges. On letter D, we have the limit as n approaches infinity of n over 1 minus 2n. And we're going to use our ending behavior rules. We could do L'Hopital's rule also. And this one is going to be negative 1/2. This one converges. On letter E, we have the limit as n approaches infinity of natural log of n over n. That is infinity over infinity. So in this one, we will do L'Hopital's rule. We have limit as n approaches infinity of 1 over n over 1. The derivative of n is going to be 1. This is 1 over infinity. This is 0. So this one converges. On letter F, we have the limit as n approaches infinity of n factorial over n plus 2 factorial. Well, we have infinity over infinity. We don't really know what the derivative of n factorial is, so we have to come up with a different way to solve this one. Let's pick a random number, let's say 6. So maybe we're looking at 6 factorial over 6 plus 2 factorial, which is equal to 6 factorial over 8 factorial. Well, that's the same as 6 factorial over 6 factorial times 7 times 8. The top will be 1 times 2 times 3 times 4 times 5 times 6, and the bottom will be, this will be the 1 times 2 times 3 times all the way up to 6, then times 7 and times 8, which is the same as 8 factorial. Well, look what happens. These 6 factorials cancel out, and we have 1 over 7 times 8. Well, let's apply that to not just a specific value, but let's apply it to the n's. We have the limit as n approaches infinity of n factorial over, we could have n factorial times n plus 1, and then n plus 2. In our example over here, the n plus 1 would be 7, the n plus 2 would be 8. Well, the n factorials are going to cancel out. We have the limit as n approaches infinity of 1 over n plus 1 times n plus 2. Well, if we FOILed that out, we'd have an n squared down there, And really, we have 1 over infinity, which is 0. So this one converges. Now let's compare that to letter G, where we have n factorial over n minus 1 factorial. We have the limit as n approaches infinity of n factorial over n minus 1 factorial. Well, let's pick a specific value. How about 6 again? 6 factorial over, now n minus 1 will be 5 factorial. That's the same as 5 factorial times 6 over 5 factorial. These will cancel out, and we're just left with 6. Let's apply that same kind of theory to this one. We have the limit as n approaches infinity of, now we're going to have n minus 1 factorial times n, and that's kind of right here. There's n factorial, and then times n minus 1 factorial times n over n minus 1 factorial, which is the limit as n approaches infinity. These are going to cancel out, and you're just left with n. Well, that's shooting off to infinity, so this one diverges.